Hello, and good day to everyone. My name is Gelo, and today I want to tell you about the transitivity of entanglement. This is joint work with the people shown here. The next few minutes, I want to describe what is the transitivity of entanglement, how do we certify it, give some example of some state that displays it, and in the end, we will consider questions that go beyond transitivity. I like you to think of transitivity as some notion that is complementary to monogamy. In monogamy of entanglement, if we have A, B, and C, the entanglement between A and B restricts how much entanglement you can have between A and C. However, for transitivity, we want to consider the situation where AB, AC, and BC are all entangled. Here's how we define it. If A and B are in some entangled state sigma, and A and C are in some entangled state tau, we say that we have entanglement transitivity if for all joint states rho A, B, C, we have that B and C is always entangled. Now, for any pair of entangled states sigma and tau, we can test whether they will display transitivity or not by computing the following semi-definite program. If this SDP returns a negative value, then sigma and tau will show transitivity. This is because this SDP tests whether all the joint states rho ABC will have a negative partial transpose in the BC marginal. Transitivity can be asked not just for 3 parties, but also for n parties. You can specify k marginals involving subsets of these n parties. And then you can ask if the pair 1n is entangled or not. We should emphasize that transitivity is about the marginal states. We don't need to know what is the global state. It's worth mentioning here that if you consider the dual problem to our SDP, it says the transitivity is equivalent to some two-local Hamiltonian problem. In particular, sigma and tau will have some joint state rho ABC, and this is the ground state of the Hamiltonian that we are trying to find. Now let's consider some examples. So here I have a 6-qubit state. I specify the state of certain pairs. Here I choose 1, 2, 2, 3, and 3, 6 to be in some state sigma, which is a mixture of some Bell state and some pure separable state. And we ask, is the pair 1, 6 entangled? And you compute the STP. It says it has a negative value. Therefore, the answer is yes. And it's worth noting in this example that we didn't need to specify marginals that involve qubit 4 and 5. And this is the case for transitivity. You can answer it with limited marginal information. Now, if we go beyond, then we can ask questions where the marginals are not all entangled. For instance, I could choose sigma AB that's separable and tau AC that's entangled, and then ask, will the BC marginal always be entangled? Or if you have n parties, you can specify the state of certain pairs, and then ask, are the other pairs going to be entangled? Finally, we considered entanglement here, but it's clear that you can replace it with other resources. For example, if you have the fully entangled fraction of a bipartite state being bigger than 1/d, we say that it's useful for teleportation, and you can ask transitivity for that. So this is the summary of what I've told you today. That's it. Thank you for your attention.